Okay, welcome back, everybody. Just a couple of quick things. One, don't forget the exam today. It will shut down at 11:59. It is open now. It's time for 75 minutes. Straightforward, nothing. Hopefully, no questions and trying to surprise you in. It's just straightforward questions. If you look at a good resource, I've been asked before, but a good resource for these exams are the overview file in each module. In that overview, it will give you examples. It tells you what we're going to talk about for that chapter. And then at the end, you also have a worksheet for every module. Those worksheets in the overview is a good source to give you an idea of what kind of questions you'll be asked, okay? Variety, multiple choice, short answer, short answer, like short essay. That's about it, nothing out of the ordinary. So give yourself plenty of time, your time for 75 minutes. So, please don't wait till like 11:30 and then try to take it. So, and once you start it, you can't get out of it. Okay, that's what the whole browser, lockdown browser is all about. Also, it kind of keeps you in the browser. It does make note if you go out of the browser, so I'll be looking at that. Don't forget the two, if you need, which hopefully you already printed out, is the periodic table and the shapes table. That one, of course, you can use it there, but don't use the electronic version because the lockdown browser will think you're going out of the exam to take a look at it. So that's why we suggest you print it out and have it there for yourself so you can look at it. All right. Any questions about chapters 1 to 3? Any questions you may have? What I'm going to do today is I'm going to finish this chapter, which is 5. And then the next chapter is your periodic table, which is kind of short. And we'll jump onto that one and finish that one. And then whatever time is left, I would remain here. And if you have any questions, feel free to bring them up concerning exams or anything else. So the rest of the time will be used for office visit, okay? All right, because I expect we're almost done with this chapter 5. We're in slide 39. So there's like 3 or 4 more slides. And then the next chapter, which deals with the periodic table, is about 24, 25 slides, which again is also short, okay? And so we'll probably knock both of these out within an hour, hour and a half, and then whatever time is left is open up to whatever questions you may have, unless you have questions now. No? All right. Let me share the screen and start off where we left off. I wrote down that we ended up in slide 39, but let me back it up a little bit, okay? Now, the challenge I think that most students have with this particular chapter is the concept of the electrons and where they're at with our model. Okay, we established that the atom in the center is the nucleus, okay? And in the nucleus exists the proton and the neutron, okay? That we've established that. Then based on the emission spectrum of different elements, that is, we had sealed tubes, like fluorescent tubes, filled with different elements, and then we excited them with electricity, basically making fluorescent tubes, and then analyzing the light that it was emitted, running it through a prism, which the prism broke the light up into their different wavelengths. We ended up with the emission spectrum that all the elements have. And the emission spectrum, what that represents, are the energy levels that these electrons existed. Prior to that, our model was, okay, we got the center nucleus, proton, neutron, and then the electron was somewhere around orbiting somehow, okay? Once that information came about with respect to the emission spectrum, then we got a clearer picture that these electrons exist in very specific energy levels. And so we have 7 energy levels denoted by, if you look at the periodic table that you have, and if you look on the left side here, I have marked, let me get this. From on the left side, I have marked 1 through 7, okay? Those represent the energy level. So energy level number 1 consists of the electrons of hydrogen through helium, okay? Energy level number 2 starts with lithium, goes all the way across the periodic table through neon. So those are the electrons that as we build up electrons, we start off at the first energy level. We fill up those energy levels first. And then as we increase the element, we increase the number of electrons. So those electrons will go into the second energy level, okay? But more information. And we continue. We go, all the way to the next energy level, okay, so on and so forth. So argon, for example, has 18 electrons, and they fill up energy level 1, 2, and 3, okay? If we go to the fourth energy level, and I'll stop it here, all the way from potassium across to krypton, krypton has, see on the far right, has 36 electrons. And so we fill up energy level 1, 2, 3, and 4. So we sequentially fill up these energy levels to begin from the lowest to the biggest, okay? And so you can see one of the trends of the element with respect to radius is as we go down the periodic table, the element gets bigger. We get a larger energy level. So potassium over here, number 19, is much bigger. It's an energy level number. Here's potassium right there. Number 19, it is an energy level. Its outermost electrons, its outermost energy level is the fourth. And we compare it to, let's say, lithium, where lithium's outermost energy level is the second energy level, okay? So lithium is much smaller with respect to potassium. So going down the periodic table, the atoms get bigger, okay? That's your first trend. All right, so from that, we continue with the energy levels in this direction, but now we find out that within each energy level, there are sub-levels, okay? Sub-levels. So the first energy level only has one sub-level. These sub-levels we call orbits, okay? So the first energy level only has what we call, there's 4 sub-levels. We call the S, okay, the P, the D, and the F orbits, okay? So the very first energy level, the only orbit they have is the S, as in Sam. And so hydrogen has 1 electron, which exists in 1s superscript 1. That electron says that configuration 1, not configuration, but that notation 1s superscript S is telling you that hydrogen's electron, its sole electron, occupies in the first energy level, specifically in the S orbit, and there's 1. So we would write the electron configuration for hydrogen as, okay. I thought I could write it, but I can't because my pen. Okay. As for hydrogen, it would be 1 S superscript 1, okay? So the 1 represents the first energy level. We're talking about hydrogen right here. There's only 1 electron. And the superscript represents the electron in the S orbit. As we go across to helium, Then for helium, its electron configuration is 1s2, okay? 1s2, telling you that for helium, which only has 2 electrons, okay, those 2 electrons occupy the first energy level and specifically in the s orbital. And for helium, there's 2 electrons, so we get a superscript 2. So note the difference in the electron configuration between hydrogen and helium, 1s1 versus 1s2, okay? Now, as we proceed to go to the higher and the larger elements, we go to the second energy level. Okay. Now, if you notice here that we're in the second energy level, that I have put marks, I have labeled the elements in specific area as either the S elements, okay, which represent the first 2 columns, okay, the first 2 columns. So this group here will be 1s1, and this group here will be, well, I shouldn't say 1s, but it'll be xs1, x, and s2. The X represents what energy level it is. So hydrogen had 1s1, okay? Lithium would be 2s1. The sodium would be 3s1, and we're talking about the outermost shell, okay? Now we go across here, starting with group 3A, going down the periodic table. At this point, we call these the P elements. So we got P, all these that are highlighted here in yellow, starting with group Roman numeral 3A, all the way across to the last column, okay, right there. Now notice there are 6 columns. So the 3A, that's where the p orbits goes into play, because at the second energy level, whereas the first energy level, we only have 1 orbit, that was the s. In the second energy level, we introduce 2 orbits. We got the s, well, let me make sure we got the s as in Sam and the p. Okay, the first 2 columns over here are the S, S1, S2. We shoot across, starting with group number 3A, we got P, we go P1, P2, P3, P4, P5, P6 across the periodic table. So P1 all the way across to P6. Notice we didn't put a coefficient because that coefficient depends on what energy level we're talking about. Where did it go? There we go. So P1 all the way across to P6, all right? And the coefficient depends on the number over here, 1, 2, 3, 2, 7. Now, on the third energy level, we continue to have the s orbits, which is 3 starting with sodium, and we go across the periodic table, okay? And we continue 3s1, 3s2 as we go across the periodic table. And then we introduce the d elements, the d orbits. Now, they're in this energy level 3, but these electrons come from the elements that are in the 4th period. Okay, so starting with SE, which is element number 21, notice that there are 10 columns here. We're going to call it D1 on the far left and go across to zinc would be D10. Okay, so D1, D10 all the way across. You would think, okay, that Ds would be in the same energy level that element's in, but that's not the case. because of the mathematics involved, it turns out that these elements are actually one energy level less than the energy level that they're in. So the d orbits for SC element are actually in the 3D level. So actually starting with number 21 for the d elements, it would be 3d1. Sorry, my pen is not doing so good. And 3d10 as you go across the periodic table from Se to zinc, okay? And that's just the nature of the beast, that those orbits are one less energy value than the level that they exist, okay? But we don't have to worry about the d orbits until you get to element number 21. So prior to that, you're going across from, in the third energy level, you're just using the 3s and the 3p's, okay? Now, with the fourth energy level, you start potassium, you got 4s1, 4s2 as you go across the calcium. And if we start with Se, if you wanted the electron configuration, now we start with the d elements, okay? So Se for the d will be 3d1 because it is one energy level less than the energy level that is in. The F elements down here in the bottom, it's very similar. Okay, these are, there's 14 columns across down here, but there's, notice here the group starting with Se is in group 6. And again, you would think that the F orbits, that's where these elements got the F orbits, but they don't come into play until you get to element number 59. You would think that the F orbits would be in the same energy level that they exist, but they don't. The F orbits here are actually 2 energy levels in less than the energy level that they're at. So for this particular one, for number 59, instead of 6F1, it would actually be 4F1. And we do that all the way across. So it would be all the way across, it would be 4F14 as you go across that row, okay? The ones in row 7, it would be 5, okay? So you subtract 2 from the energy level it's in, and that represents the energy level for the F orbits. So for the Ds, the D orbits are one less energy level than the energy level that the element's in, one less. And the F, it's 2 energy levels. Now for the S and the P's, straightforward, whatever energy level they're in, that's the energy level that they're in. Now for S's, everybody has an S orbit from 1 through 7. For the P's don't get introduced until the second energy level. So starting at the second energy level, you got 2P down to 7, okay? And the D's don't come into play until the 3 energy level. So 3D and then 4F for the F orbits. Okay. Now, having this big mess here, what this does is, I think that it really, you can use the periodic table and the position of the element to write the electron configuration for whatever element you have by seeing its position on the periodic table, okay? For example, let's do an example. All right, let's do aluminum right there. So the thing is, we're going to write the electron configuration for aluminum. Now, if we look at where aluminum is in the third energy level. That is the outermost shell for aluminum. It's in the third energy level. So that means that the first energy level is full and the second energy level is full. And there are 13 electrons for aluminum, atomic number 13. So there's 13 protons, 13 electrons, all right? So to write the electron configuration, we can, since energy level 1 is full, we can quickly write 1s2. Okay, so that takes care of 2 of the 13 electrons. So we had 13. Okay, subtract 2, we got 11 electrons left to put someplace. Well, this first energy level is full. So now we go to the second energy level. That tells us we have S and the P orbits. So we got 2s2, and when the second energy level, all the P's is full, 2p6. Remember, for the P's, maximum number of electrons you can put in the P's is 6. Maximum for the S is 2. Maximum for the D's is 10. Maximum for the F's is 14. So we got, took care of 8 more, okay? 8 more electrons, which happen to be in the second energy level, okay? So now we got 3 more electrons to put someplace. Okay, the fact that it is in the third energy level, that tells us that we go across the periodic table. 3s2 is full. And then aluminum exists in the P elements, very first column. Okay, so that's 3p1. So notice there's 2 electrons, 2 in the S, 1 in the P, and that takes care of all my electrons. I have 13 electrons, okay? Of the 13 electrons, the outermost shell is in the third energy level. So there's 3 energy levels for aluminum. First one, second one, and third one. Of those 13 that aluminum has, 3 of them are in the outermost shell, what we call the valence shell. Of those 3, 2 of them exist in the S orbit, and 1 of them exists in the P orbit. Also, notice the Roman numeral 3 up here. That also tells you how many valence electrons aluminum has. In fact, that tells you how many valence electrons that everybody in that group has. Okay, so the outermost shell has 3 valence electrons, and then the inner shell, the second energy level, is full, and the first energy level is full. Okay, if we wanted to go to silicon, which is just 1 more electron next to it, all we got to do is change that to 3p2. And if we went to argon, we just go 3p6. We just sequentially just add them up, put them into their particular order. Okay. All right, so that's how we can use the periodic table to very quickly write the electron configuration for these elements. Now, there is a shorthand way to write the electron configuration, and you can write the shorthand way. If the question says don't use a shorthand way, then don't present that shorthand method. But if it doesn't say anything about that, then you can present the electron configuration in a shorthand mode. All right, so we're still doing aluminum, okay? All right, point number 1. So what you do to do the shorthand, you find the noble gas, that's these guys in groups 8, the last one, behind the element. So we work backwards from 13, and the noble gas is neon, okay? So for aluminum, the electron configuration in the shorthand way is we write neon, Ne, and then we put brackets around neon. What that represents are those 10 electrons for neon, okay? Then we see that aluminum is in the third energy level, so we go across, 3s2 is full, and then 3p1, okay? So that is the shorthand way of writing the electron configuration for aluminum. Okay. We put the noble gas, the last noble gas, behind whatever element that is. So even if it's chlorine, if we were doing electron configuration for chlorine, okay, let's assume this is Cl, chlorine. same neon gas, but then we would go 3p1, 2, 3, 4, 5. So this would become the electron configuration shorthand mode for chlorine. Neon brackets 3s2, 3p6. Okay. All right. So yeah, it's okay to use the, don't forget the brackets, not the parentheses, but they're brackets around the noble gas. All right, so my recommendation is take your product table and label them like I've written here, so that will help you out with respect to doing the electron configuration. All right, so if we look at the electron configuration, and this is going to give us an idea as to why certain elements lose electrons and certain elements gain electrons. The ultimate goal in the chemical reactions is to have the octet, to have 8 electrons around the outermost shell. That's the most stable configuration that exists with respect to these elements. Once it obtains that octet fulfilled, it's in a stable state. Okay, so if we look at sodium, and we do the electron configuration for sodium, it is 1s2, 2s2, 2p6, 3s1. Note on the periodic table that sodium is in group 1a, the first column. The thing that all these elements have in common, okay, is they have 1 valence electron in the outermost shell. Okay, this is important here. All right. What everybody has in common within a group, we call that a group. Within this group is the number of valence electrons. And this only is true for those elements that are listed, the A elements, have a Roman numeral and then followed by an A. That is not the case for the B elements, okay? The B elements can exist in multiple formats, or what I call formats, actually multiple charges, okay? So we can't predict it, only the A. And so by looking at that Roman numeral up there, it will tell us how many valence electrons are in that element. And so everybody in group 1A, regardless of how many electrons they have in total, will have 1 valence electron in the outermost shell, okay? And the same is true for the elements in 2A. Magnesium, right there, has 2 valence electrons in the outermost shell. And then we go across to the P elements, we start off with 3A, there are 3 valence electrons in the outermost shell, valence shell, all the way across to the periodic table where they have 8, except helium. Helium only has 2 because it only has 2 electrons. But everybody else, neon down, has 8 valence electrons. The ultimate goal for all these elements is to be similar to a noble gas. That's that last column on the right, 8A. And that is to either have 2 valence electrons, and there's only one. Hydrogen's goal is to have 2 valence electrons around it, like helium. And everybody else, their ultimate goal to be more in the stable state is to have 8 valence electrons around the outermost shell. That is the goal there, okay? All right, so let's go back to sodium. You can see here that sodium is in group 1A, and it has 11 electrons total, okay? One of those electrons exists in the 3s1 orbital in the outermost shell, its valence shell, okay? Now here's the thing. As the ultimate goal is to get to the octet configuration, 8 valence electrons. Now, in the third energy level, we can put more electrons in there. But from an energy perspective, for sodium, it is easier to lose that one electron that's sitting there out there all by itself in the outermost shell than it is to pick up 7 more. It's not from an energy perspective, it just can't handle 7 more, okay? It would be very difficult, so it just wants to give it up. And that's what happens with all metals. That's why I said all metals, put this in long-term memory, all metals want to lose electrons. Okay. Whereas the counter to that is all non-metals want to gain electrons. So let's talk about the sodium here. So sodium wants to lose electrons. And when it does that, right now it has 11 protons, 11 electrons. It is neutral in charge. I got 11 positives and 11 negatives. Okay. Now, when it loses that one electron that's sitting there all by itself, okay, it now has 11 protons, 11 positives, but now it has 10 negatives, okay? So I got 11 positives and 10 negatives. The difference is I have 1 positive left over, and that is the charge of the sodium ion. Okay, this is the sodium element with no charge, the atom. When it loses an electron, it's going to be now become an ion. And that is, the ion is what you put on your French fries. That's what you're shaking in there, sodium chloride. You're looking at the ion. Look at the electron configuration now. The new valence shell is in the second energy level. Why? Because that electron that was on the third energy level is now gone. So the next level is in the second energy level. And look at how many electrons it has in the second energy level. There are 8 electrons in the new valence shell, which is the second energy level, which is the ultimate goal that elements want to do. They want to obtain that magical 8 number. Now, can you, based on this information that you just have, I just gave you, when I compare the atom to the ion with respect to diameter, what do you predict will be bigger, the atom or the ion of sodium? Who's going to be bigger in diameter? What do you think? What is your conclusion based on what we just talked about, how sodium lost an electron? What can you say about the radius now of the ion? Would you anticipate the radius of sodium plus to be bigger or smaller than the atom? What do you think? Go ahead, make a prediction.
Smaller?
Smaller, exactly. Because, sodium atom starts off with 3 energy levels, okay? And if I were to kind of draw it a little bit, I don't know, I got a cross-sectional. Here's the 1, the 2, and the 3. And so we have 2 electrons in the first energy level for sodium. The second energy level has 8. And then the third energy level has 1 electron. That's the outermost shell. Okay, that is the atom. Now, the moment you lose, so you have a radius, it's 3 energy levels. Now, the moment it becomes a ion, well, that electron in the outermost shell is empty now. And so now the new shell is in the second energy level, and obviously it's smaller, okay? So the radius of the atom of the ion is the radius compared to from the atom versus the ion is that the atom is much bigger than the corresponding atom. And this is true for metals, okay? You might say, well, wait a minute, what are you talking about metals? Let's go refresh your memory here. The stair step sitting here, right here, this stair step, Everything to the left of the stair step are metals except hydrogen, not hydrogen. Hydrogen's not a metal. Everything to the right of the stair step are non-metals. And then on the stair step, we call those metalloids or semi-metals. They have properties of both metals and non-metals, okay? And so all metals, that is to the left of the stair step, want to lose electrons, okay? And all nonmetals want to gain electrons. That's their preference. And if you think about it, all these nonmetals right here, starting with nitrogen and to fluorine, they're much closer to the noble gas here, in this case, neon, compared to the metals that are beryllium and lithium, who are further away from the noble gas, all right? And they're to the left of the stair step. And so being metals, they're gonna lose electrons much more readily than the nonmetals like nitrogen, oxygen, and fluoride that want to gain electrons. And in doing so, they now have the same electron configuration as the noble gas in front of it, in this case, neon, okay? Phosphorus, sulfur, and chloride, when they gain electrons, they are now have the electron configuration of argon. I repeat, they have the electron configuration of the metals in front of them. They don't become the metal in front of them, okay? They share the same number of electrons. They don't, in other words, chloride, sulfur, and phosphorus, by gaining electrons, do not become argon. No, they're still chloride. They share the same number of electrons as that noble gas. And when the metals here lose electrons, specifically, everybody, the 1A and the 2A metals, they, by losing 1 to 2 electrons, they now have the same electron configuration as the noble gas behind it. The ultimate goal being that they have that magical 8 number again, okay? And also the radius drops, becomes smaller when they become ions. All right, now with respect to nonmetals, let's take a look at sulfur. Sulfur is on the right of the periodic table on the stair step. It is a nonmetal, and like I stated, nonmetals want to gain electrons. So let's look at the electron configuration of sulfur. It has 16 protons and 16 electrons. If we look at the valence shell, which is highlighted here in yellow, you can see that there are 6 valence electrons for sulfur, okay? So it's in group 6A. So all it needs is 2 electrons to fulfill that octet rule, okay? And those 2 electrons will fit quite well in the p orbit, because they're in the p, remember, you can put in 6 maximum. So there's 4 in there right now. So there's room for 2 more, okay? Sulfur is a nonmetal, so it's going to pick up electrons. Specifically, it's going to pick up 2 because it has room for 2 in the p orbit. And that's why learning to write the electron configuration helps you to understand why some elements gain 3 electrons, some gain 2, and some gain 1, okay? In this case, group 6 elements, everybody in group 6 elements needs 2 electrons on nonmetals, and they're going to gain those 2. And in doing so, it went from 16 protons to 16 elements with respect to the atom. And when it becomes an ion, here's the deal you got to remember. When we gain or lose electrons, you are creating an ion. That ion could be either positive charge or negative charge. And they're going to have their own specific name here in a bit, but right now the generic name is ion. So now sulfur has picked up, it still has 16 protons, but now has 18 electrons. So I got 16 positives and 18 negatives. My net now is a -2 because it picked up 2 electrons. And the electron configuration now is full. there are 8 electrons around the sulfur ion. And you know what else? What happens? For nonmetals, we change the name. For metals, when they lose electrons, like here, we just say either to distinguish between the atom and the ion, we just say for the metal, we just say sodium atom or sodium ion. Okay, that's all we do. For the nonmetals, and this is to preparation to give you to start learning nomenclature and naming, we go from sulfur, which is the name of the element, and when it becomes an ion, the name gets changed to sulfide. Okay? Sulfide is different from sulfur. Sulfide is the ion. Okay? We're going to learn that all the nonmetals will change its name when they become ions. Let's go back to productivity. So if we're starting with nitrogen, oxygen, and fluoride, nitrogen becomes nitride, oxygen becomes oxide, fluorine, I should say, becomes fluoride, okay? Phosphorus becomes phosphide. Sulfur, we just talked about, becomes sulfide. Chlorine becomes chloride, okay? And so forth and so forth. We got the bromide and the iodide, selenide, and telluride. But when they gain electrons in just a single element, they become whatever element, IDE. So the IDE tells you it's just the element itself. Thing to remember is when we look at down here, where we've got the polyatomic ions, it is sulfur, but attached to sulfur is oxygen. And this unit here, where you got 4 oxygen atoms bonded to the sulfur and overall negative 2 charge, it has a name called sulfate. And there's a sulfate, and then there is a sulfite. The only difference between the 8 and the ite is the 8 normally has 1 more oxygen than the ite. Okay? We're going to learn more about that in time. So for sulfur, just to give you an idea, you have the element, which is called sulfur. You have the ion of sulfur itself, which we now name sulfide. And then you got the polyatomic ions of oxygen with sulfur, where you go sulfate and sulfite. These names are important because you could be given the name of a compound, like sodium sulfide, and we're going to learn how to take that name and break it down into writing the formula for that name. Okay, so naming is crucial. Okay, now note here that it gained 2 electrons, the sulfur, to become the sulfide. Now, from your perspective, when we look at the radius of the sulfur, be it the atom or the ion, what would you anticipate that the radius would be? Who would be bigger, the atom or the ion? Like we talked about the sodium ion, we learned that the ion itself becomes smaller, but what about the case here? What is your thought process tell you? Who would be bigger with respect to sulfur, the atom or the corresponding ion?
The ion?
Exactly, the ion would be bigger because look what happened to it. The ion picked up 2 electrons, 2 more electrons. They're negative charge, whereas before there were 6 electrons negative on the outermost shell, and now there's 8. And being negative charged, they're going to repel each other. So adding 2 more is adding more like two more people in, 2 more cars into the traffic. It's getting crowded now. plus their negative charge, they're going to repel. So the ion of the element that gained electrons would be bigger in the radius than the atom itself because it picked up 2 electrons and they occupy more space, okay, because of their charge. All right, now in this scenario, they're asking you to write the electron configuration. But the thing to remember, you've got to make sure that you are writing the electron configuration of, in this case, notice that everybody here is an ion, okay? There's a difference between writing the electron configuration for potassium. Okay, so let's do potassium. Okay, potassium is in group 4. So we can go 1s2, 2s2, 2p6, we're going across, and then we go to 3s2, 3p6, and then it's in group 4. So we go 4s1, first element. See? I did that simply knowing its position in your product table. And that is for the atom itself. But here they're saying +1. So what's happened is you were talking about the ion. So that means that that electron has been lost. Okay. And so the electron configuration of the ion will be 1s2, 2s2, 2p6, 3s2, 3p6, okay? Because the ion has lost that outermost valence electron from the atom, okay? Now it has the same number of electrons as argon. And so what we say, we use the term isoelectronic, meaning they have the same number of electrons as some other element. So the potassium ion, this is the ion, is isoelectronic with the argon noble gas by losing 1 electron, okay? Now, look at nitrogen here. Nitrogen has a -3 charge. Find out in the product table, you see that nitrogen is in group 5A, okay, on your product table. Nitrogen is a nonmetal, which further tells you that nitrogen will gain electrons. And being in group 5A, Roman numeral 5A, tells you that it's only 3 electrons away to get that magical 8. So nitrogen will gain 3 electrons, okay? And in doing so, now becomes isoelectronic with neon. That is the electron configuration of nitrogen, 1s2, 2s2, 2p6. Normally, nitrogen would have been atom itself would have been 2p3, okay, 2p3, 5 valence electrons. So it's a nonmetal, it has room for 3 more electrons, it will pick up 3 electrons. Guess what? How we talked about changing the name, what do you think the nitrogen's new name would be once it becomes ion? What is the name of this ion right here? Okay.
Nitrogen.
No, it can't. Nitrogen is the atom.
Nitride.
Okay. There you go, nitride. So now we change the name to nitride, just like we did with oxygen to oxide, sulfur to sulfide, fluorine to fluoride, chlorine to chloride, bromine to bromide, iodine to iodide, okay? So the IDE tells you we're looking at the ion. All right, now we got magnesium. And its electron configuration is isoelectronic, guess who? With neon. Whereas nitrogen becomes isoelectronic with the noble gas in front of it, in this case neon, Magnesium, once it's a metal, it's going to lose electrons. That's why magnesium has a +2. It's going to lose electrons to become isoelectronic with the noble gas behind it, which is neon. And so the nitride ion and the magnesium ion, what they share is the same number of electrons as the noble gas neon. And now both of the ions have the octet fulfilled. The outermost shell, in both cases, it's in the second energy level. There are 8 valence electrons, which is that magical 8 I keep talking about, that came from all the mathematics in this model, that is the stable state for elements, and that's the driving force for chemical reactions, be it ions and be it another type we're going to talk about. We're going to electrons that are shared. The ultimate goal is to get that octet. Okay. All right. So the takeaway here is when they ask you for electron configurations, make sure that you are looking carefully at the element and make sure you not give the atom electron configuration when in fact the question is asking about the ion. Okay. All right. So here we're talking about ionic charges, which we've kind of introduced to you. And it's also related to the group that they're in, the group number, the A group. So group 1A, group 2A, and those are the first two groups in their periodic table. Point number 1 is they're metals, and being metals, they tend to want to lose electrons. Now, hydrogen is not a metal, but it is in that position. Let me share the periodic table with you. Okay, let me explain why. See, hydrogen here is not a metal, but it has a tendency, it does have 1 valence electron. Okay, it's the first element, only 1 valence electron. So it shares the number of valence electrons as all of the other elements in group 1A. It also shares that capability of hydrogen losing that electron to end up with a positive charge, which we're going to talk about at length. That positive charge is called a proton, which makes things acidic. So because of that nature of hydrogen, it is placed in the first group because it has that 1 valence electron, which shares that property with everybody else in that group. And second of all, like everyone else in that group, it will lose that 1 valence electron. Okay. On the other end of the spectrum, it also, because it's a 1s1, it has a capability of gaining 1 electron. So some periodic tables, you'll find hydrogen sitting right here in this group. And what happens there, because it has 1 valence electron, by gaining 1, it now is isoelectronic with helium. And so the duet has been fulfilled. So hydrogen can gain 1 electron or can lose 1 electron. It's a very unique species. Anyway, that's the thing about hydrogen. So everybody in group 1 wants to be like a noble gas, okay? So hydrogen, exception of hydrogen, but all the other ones, all the other metals, by losing electrons, specifically, they're going to lose that 1 because all they got, 1 valence electron. And in doing so, they will be isoelectronic with the noble gas behind it, okay? For example, lithium right here. Oh. Lithium, by losing 1 valence electron, it's got 3 electrons altogether. By losing that 1 valence electron, it now becomes isoelectronic with helium. Okay. Sodium, by losing 1 valence electron, becomes isoelectronic with neon, and so forth. Potassium, right here, losing that one valence electron, now becomes isoelectronic with argon. Okay. Now, at the other end of the spectrum are the nonmetals. Change their color. And so nitrogen, oxygen, and fluoride, by gaining respectively 3, 2, and 1 electrons, become isoelectronic with neon. Phosphorus, sulfur, and chlorine, by gaining respectively 3, 2, and 1 electrons, becomes isoelectronic with argon. Plus, we also change the name. Okay, so nitrogen becomes nitride, oxygen oxide, fluorine becomes fluoride, phosphorus becomes phosphide, sulfur is sulfide, chlorine is chloride. And the other two that are more often used than the others are bromine and iodine. Okay, they gain 1 electron and they become respectively bromine becomes isoelectronic with krypton, and iodine becomes isoelectronic with xenon by gaining that 1 electron. Okay, so the goal, the ultimate goal, is to become or have an electron configuration as a noble gas. They call them noble gas because they're very unreacting. Noble gases do not react with other species very readily. Why is that? Because the octet is fulfilled. It's happy and stable. It's not going to lose any electrons, nor if it's going to gain, because there's no room to gain it. It has to go to the next energy level, which from an energy perspective is not very stable. Okay? All right. So group 1A's would be end up, the ions would be a positive 1. Group 2A, positive 2. All right, you're going to lose 2 electrons. All right, so the ions here for group 1A would be a positive 1, group 2A, positive 2, and group 3A, positive 3. Positive because, one, we're talking about metals, and there are no non-metals in these groups. They're all metals. And being all metals, they want to lose electrons, okay? So magnesium will always end up with a +2 charge. Now, if you write +2 or 2+ makes no difference. You can write it one way or the other, all right? All right, so group 7A, okay, because they're in group 7A, and they are only 1 electron away to get that 8 electrons around it, they're going to gain 1 electron, so end up with a negative charge, a -1 specifically. Okay, so chlorine becomes chloride with a -1. Group 6A is going to pick up 2 electrons. Okay, group 6A, Roman numeral 6. I'm only 2 away. I'm trying to get to 8. I need to get pick up 6 electrons, the nonmetals, and I end up with a -2. Excuse me. So oxygen goes to oxide with a -2. All right, so the point here, and then group 7A, -1 charge as explained, group 6, -2, group 5, the nonmetals will pick up 3 electrons and end up with a -3 charge, okay? So nonmetals want to gain electrons and become negative ions. The name for negative ions specifically is right there, anions, okay? For positive, they call cations. That's how we distinguish. The term ions is generic, could be a positive ion or negative ion. But you use the term anion, it's specific. Anions are the negative charge ions. Cations are the positive charge ions, okay? So metals become cations with the positive charge. Nonmetals gain electrons, become anions. Now, group 4, okay, group 4 is in the unique position. Let's go to group 4 in the periodic table. All right, so we can show that. They're in the unique position as these guys right here. Well, think about it for a second. They have 4 valence electrons in the outermost shell, carbon, silicon, down the road, okay, down the group. 4 valence electrons. That puts them in a very unique position because now what can happen is they can either, from an energy perspective, losing those 4 or gaining 4 more to get that magical 8 is equal. And so they can gain 4 electrons or they can lose 4 electrons. The ones in group 4, they're on the fence, if you will. So on the fence depends on the reaction conditions if I'm going to lose or gain. Anything over 5, so 5 forward, 5, 6, and 7, Roman numeral 5, 6, and 7, they gain electrons. Anything less, group 3, 2, and 1, lose electrons. Okay, and the ones on the fence, group 4, depends on reaction conditions. So that what that means is that they can have a charge that can vary all the way from a -4 if they gain 4 electrons, or so I got a -4 to a +4, where they can either lose the 4, which gives them a +4, or gain 4 more, which will give them a -4. Okay. Very unique position. And of course, group 8A, they're stable, no more gas configuration, except helium, which is a 2, not 8. Okay. And that's what we're striving for. So this number here, these numbers here kind of give you an idea of going from group 1A from the far left of the product table to the far right, which is 0. So +1, +2, +3, group 4 could be positive or -4. And then after that, we start gaining electrons, -2, -3, -2, -1. Okay. What we're trying to do here, what we're going to be doing, notice we started with the elements that are neutral. Okay. We talked about the electrons and where they're at, and then we talked about the valence shell. And we talked about the ultimate goal is to get to that magical 8. And in doing that, to get to that 8, I'm either going to lose electrons or I'm going to gain electrons to make these ions. Once I make these ions, I can start putting them together to make compounds. Okay, I can put positive and negative rich. Remember that. I won't be able to. Normally for Chem 130, we won't be putting together 2 negatives or 2 positives to make a compound. It's always going to be a positive and a negative. So like sodium and nitrite, sodium or potassium and oxide to make a compound. Okay, that's what we're going to be doing here in a little bit. Okay, here's a list of elements. Okay, and they're asking you what is the charge that they will become. And to answer this, you simply look at where they're at on their product table. And second of all, to verify that either if they're metals, they're going to gain electrons. If they're non-metals, they're going to lose electrons. So, you know, I could go here and discern which ones are metals, which ones are not metals. So lithium's a metal, so it's going to lose electrons. So it's going to have a positive. Okay. Magnesium also is a metal. It's going to have a positive. Sulfur, it's going to be a negative charge because it's a non-metal. Bromine is also non-metal, so it's going to end up with a negative charge. And nitrogen also is a non-metal, therefore will have a negative charge. And then finally, aluminum is a metal, so it's going to lose electrons. So the non-metals will gain electrons, the metals will lose it. Now, the magnitude of that plus and negative depends on where they are on the periodic table. Lithium is in group 1A. So lithium would have a +1 charge. It would lose 1 electron. Okay. So its ion is lithium plus. Magnesium will have a plus charge, but it is in group 2A. So therefore will lose 2 electrons, which ends up with a +2 charge, and we write it with magnesium superscript the charge. Okay. Sulfur is a nonmetal. It's going to have a negative charge. It is in group 6A, meaning telling you that it's going to pick up 2 electrons. So it would have a -2 charge, plus its name gets changed to sulfide. Okay. Bromine is in group 7. Group 7 element. It's a nonmetal. It will gain electrons. It specifically gain 1 electron. Excuse me. Specifically gain 1 electron with a negative charge, a -1, and we change its name to bromide. And then nitrogen, it's in group 5A. It's a nonmetal. It will gain 3 electrons, okay, to have a new net charge as an anion with a -3. And then aluminum is in group 3 metal. It will lose those 3 valence electrons and end up with a -3 charge. Okay, and so we got sulfide, bromide, nitride. Okay, and then the others, the cations, are just lithium ion, magnesium ion, and aluminum ion. Now we can start putting these together. And let's put together a magnesium ion and a sulfide. Well, to put them together, we have to put them together such that the charges cancel each other out. I have to put them together such that I have enough positives to cancel out the negatives. Where you go? So I got the sulfide as a -2. Well, it's a +2 and a -2. I can simply put them together as a 1-to-1 ratio. So its formula would be MgS. Its name would be magnesium sulfide. Okay, I can do the same with the nitride and aluminum. Put them together because I got a -3 and a +3. I put them together. I can put them together as a 1-to-1. So I got aluminum, nitride. Okay. Now, if I were to put lithium and sulfide, let's say I got lithium and sulfide, I need 2 lithium because I need 2 positives to cancel out the -2 of the sulfide. So this 2 becomes a subscript. So the formula for lithium sulfide would be as follows: lithium subscript 2 sulfide, lithium sulfide. Okay. So I can do a mix and match. I got lithium sulfide, lithium bromide, lithium nitride, magnesium sulfide, magnesium bromide, magnesium nitride, etc. Aluminum nitride, aluminum bromide, so on and so forth. So I'm starting to build up a database of different compounds that I can mix and match with the cation and the anion and put them together with the right ratio so they cancel each other out to give me a 0 overall charge. And I start making these compounds, and then I've been showing you how to start naming them, okay? Because sometimes you could be asked, okay, write the formula for lithium sulfide. Okay, so here we have a metal and a non-metal, which is a very specific type of compound. We're going to learn about that here in a bit. And so I take the lithium, I break it down into the ion. So I got 1 lithium, which is a +1, right? Because I know it's in group 1. And the sulfide is sulfur with a -2, because I know it started off in group, sulfur started off in group 6, they pick up 2 electrons. So I know here, I write them in ions, and I know now that I need 2 positive for every -2. So the formula is right there. So we're going to eventually have to learn that given the formula, write the name, or vice versa. Given the name, write the formula. Okay. And this is the beginnings of that process here. Right, term again here, isoelectronic just means that it shares the same number of electrons. It is important to know that we're not saying that the magnesium ion is neon, okay? Because we know the only way magnesium can become neon, it has to lose protons. And while we're not losing protons here, we're losing electrons. You know, we can lose electrons and neutrons all day long, but that element remains whatever that element is. The moment we gain or lose protons, now we convert it to a whole new different element, okay? Because protons define that element, okay? So magnesium cation +2 is not neon. It's isoelectronic with neon because they share the same number of electrons. Phosphide would be isoelectronic with argon, okay? Because phosphorus gained 3 electrons and now it shares the same number of electrons as argon and therefore isoelectronic with argon. All right, here we have the cation, calcium +2, and then we got oxide, chloride, and the aluminum. There's the corresponding electron configuration of the ions, be it a cation or anion. Okay, don't mistake it for calcium for the element itself, because for example, if you write for S2, well, that is the electron configuration for the calcium atom. The fact that we have a +2 tells us that this has gone away, okay? And so forth with the others. Ooh. All right, so the calcium ion is isoelectronic with argon, the oxide is with neon, the chloride is with argon, and the aluminum is with neon. Now you can write the electron configuration and to figure this out, or you can find its position on the periodic table and very quickly determine who it's isoelectronic with, okay? For example, if we look at calcium, we're dealing with calcium, right? Here's calcium. It's going to lose 2 electrons. It's a metal. It's in group 2A, so it's going to end up with a +2. It's going to be isoelectronic with the noble gas behind it. And if we look at bromine, bromine is a non-metal. It's in group 7A. It has the capability of gaining 1 electron, okay? And then becomes isoelectronic with noble gas in front of it, which is krypton. Okay? And that's simply just using their position on the periodic table to be able to answer that question. All right, we'll be done here with this one here in a little bit. This one here is the elements are giving you, they want you to figure out number of protons, number of electrons, number of neutrons, okay? We know that the number of protons for selenium, Se, is 34. The mass number is given to you at 78, okay? Number of electrons, same number as since we're talking about the atom, number of protons equal the number of electrons. And the number of neutrons is simply the 78 minus 34, so we got 44. This ion is a non-metal. It will pick up 2 electrons. This is right under, this element's right under sulfur. Okay, it will pick up 2 electrons, become selenide. Okay, same number of protons. Nothing changed there, but it picked up 2 electrons. So it went from 34 to 36. And the same number of neutrons. We didn't lose any neutrons, nothing at all. We're still dealing with Se78. And then we got aluminum 27, and they got 14 protons, 14 electrons, 13 protons, 13 electrons, and 14 neutrons. When it becomes an ion by losing 3 electrons, because it is in group 3A, Roman numeral 3A, it now has 13 protons, nothing changed in the number of protons. Number of electrons have changed definitely, okay? And the neutrons remain the same. So you might come across tables like this asking you to fill out. Remember, 9 times out of 10, a lot of times the mass number is given to you up there at the superscript left. So we're talking about Se78 and aluminum 27, okay? All right, so that, ladies and gentlemen, ends chapter 5. What I'd like to do is maybe we take a quick break. Let's take a break, and then if you don't have any questions, we can continue with the next chapter. Okay. Before I begin with chapter 6, any questions? All right. Well, let us continue. This chapter deals with the periodic table and some trends that we find on the periodic table. So some of these trends we talked about already, and then be some new trends that we haven't. So anyway, periodic table is actually first developed by this scientist. He was a German scientist, Mendel, back in 1860s. Okay, what he did was arrange a table based on the known elements of the time, and he put them in increasing mass. And then he also put elements with similar properties in the same column. Keep in mind, this is way before our model that we have now with respect to electrons. So just the powers of observation, seeing that certain elements had reacted very similar. So he put them in there. It turns out, well, they react very similar because they share the same number of valence electrons and therefore share the types of reactivity, okay? He also had some holes in there, so he predicted based on this table of some elements that would be out there. And sure enough, that sent a trend there of scientists just going out there looking for these missing elements. And eventually we filled them all up and we got 118 elements. And from 92 up, or 92 back, or I should say less than 92, are naturally made. And above that, these are actually being made, actually man-made. Okay. So Moseley, another scientist later on, I don't know the exact time he did this, or Moseley, I believe you pronounce it. What he did, he created a table and where he put them in increasing atomic numbers. So this is more related or more similar to the periodic table that we utilize now. There are some changes that are trying to do. For example, the Roman numerals, they're trying to get rid of those and put some numerical numbers in there. There's pros and cons about that, but I personally like the Roman numerals. Probably that's the way I learned them, but it tells you, the Roman numerals tells you, how many valence electrons you have there, okay? Also, an aspect about the periodic table is this, that these groups here, starting with 58 and 90, they actually belong right in this area, okay? So if you were to kind of take the periodic table and open it up, you would insert the groups here that have their own name, put it in there. And I have a picture of that I'll show you, but the periodic table will be a little bit longer than we're used to seeing, okay? But they took them out and then they closed it up so you can visualize it a little bit better, the periodic table, that is. And that's what it looks like. This is a picture of the long periodic table. This is those two groups in the bottom where we call the F electrons put back in the right position and so forth. That's what they would look like. And this is what they're trying to do is to change the numbering sequence, get rid of Roman numerals and put in 1 through 18. Okay. There's been some other examples. There's been alternative product tables. There's a circular one that's been proposed of all the elements, put into a circle. Okay, here's another one here. This one here does prediction. There's an area here called the superactinides. They're predicted to exist. I do know they've been working on, I want to say element 119. They were trying to make it, but they've been pretty close, but they haven't been able to succeed. So there are people right now, scientists trying to make bigger elements. All right, so we had talked about this earlier where we said Niels Bohr introduced the idea about electrons occupying in different energy levels, specifically the S in sublevels of orbitals, the S, P, D, and the F orbitals or sublevels. And you notice that my periodic table was marked up with the S block, what we call the S block, which is the first two group, then the D block, which are the ones in blue, and then the P block, and the ones on the far right, starting with group 3A, and then the ones, the actinide, lanthanides, are the F block, okay? So notice here in the 4S group that as we go into element number 21, this is, as I explained earlier, this is the D block. We would anticipate that the electrons for the D block would be 4D, but that's not the case, that the D orbitals are actually one energy level less than the energy level that they're physically in. So that's why you got 3D and not 4D right here, and so on down the road. And for the F block, there are actually two energy levels in. And so instead of having 6F, this is really 4F and 5F, respectively. Okay. Now, the horizontal row of the product table is what we call the period. Okay. So periods, and then we have the vertical that we call a group. So the other name that's being used is family. Family's been used, but elements in the same group exhibit similar properties. And now, based on our model, it's because they share the same number of valence electrons. Okay, and therefore they have similar reactivity. Now, the elements that have the A, Roman numeral A, those are called the A group elements. And then we have the ones of Roman numerals B, especially like the D block, and the F block, those have a generic name called the transition metals, okay? The B group are called transition metals. The main group are the A group. So here the period just goes across the periodic table. It's period 2, period 5. We have, which also is the energy level, from 1 through 7. And of course, we got the groups going group 1, group 2, group 3, etc. Okay, we call these the same group, and or the term family, exhibit similar properties. Now, some of these have a more specific name. For example, the group 1A, except for hydrogen, okay, are called the alkali metals. Because except hydrogen, because hydrogen is not a metal, it's a non-metal. And then the group 2A are called the alkaline earth metals. And then group 7, where you have fluorine, chlorine, bromine, they have their own little name. We call those are halogens. You know, you may be familiar with headlights. You got halogen lamps now. They're all becoming LED, but there are some halogen lamps out there. Okay. And then you already know I talked about this at length with the group 8A, the last column, are called the noble gases. And they're called noble gases because they're very unreactive. And they're very unreactive because the octet has been fulfilled, or the duet if it's helium. Okay? So here's some columns, some groups that have their own specific name. Now the transition metals, the group B elements, or the D block, which is listed here in green, okay, these are called transition metals. Okay, we cannot predict their reactivity very well, their charge. You know, as the case with group 1 and group 2, we know that those will have all the time either a +1 or a +2 charge, and the group 3 metals will always have a +3 charge. But these metals vary. You know, for example, if we look at iron, Fe, can either be a +2 or it can be a +3 oxidation or charge. Depends. It's 2 different metals here. Copper could be a +1, or copper could be a +2 by losing 1 or 2 electrons. So these transition metals we cannot predict what their charge will be. With respect to these other ones, here, which is something you take, the big takeaway is this, that group 1A, always you would know that these guys will always have a +1 charge all the time. And the next group will always have a +2 charge. And then this group in here will have a +3 charge, okay? Those metals, you always know 100% of the time what their charge would be, okay? And then even on top of that, zinc, silver, and cadmium also will have a known charge. We'll have more on that in a second. That means that all the other ones can vary, okay? But we'll still be able to figure out what their charge will be, depending on how they're bonded together. All right, let's go to. Now, transition metals are in green. The ones in gray, and I guess that's orange color, they have a general name of inner transition metals, but more specifically, they have a more specific name series. So the lanthanide series is the top row, the one I guess in purple color here, okay? And then the actinide series are, and I guess that's orange color. Both of them are called inner transition metals in general terms, but specific terms is the lanthanide series and the actinide series. Okay? Also, the lanthanide, which is the ones in purple, are also called the rare earth metals. And then basically everybody in the actinide series are all radioactive. All radioactive. So I thought I misstated. It's 93 and above that are all man-made elements. You put them in particle accelerators and just bombard each other to create new elements. And like I said, they've been working on the new ones. As we talked about with the electrons being in specific energy levels, it's been proposed that the protons within the nucleus are also possibly in energy levels themselves. So, you know, that's research that's going on. Maybe could explain why they're having challenges trying to make more elements. Anyway, given the information I just told you, that we're up to 118. And if element 119 were created, what would you predict its period would be at? Where would we put it? Okay. What period would it be in? And what group would it be in? What would be your prediction based on what you see and see the trend here in this periodic table? Yeah, what I mean is look at number 10. Number 10 is neon. Well, when we get to number 11, we start off on a new energy level. Third energy level and go across until we get to argon, then we continue. And so number 18 is right there. And if they made number 119, where would you predict two things? One, what group would it be in? And two, what period would it be in? What would you think? Would definitely be in period number 8. It would create a whole new energy level number 8, and then it would probably be right underneath number 87. Okay, in the first group 1A, and it would more likely be a metal. Okay, based on where it would be on the periodic table. All right. Typical kind of questions that you see with respect to the periodic table that would be asked is, what is an alkaline metal in the third period, or an alkali metal? So with third period, go 1, 2, and 3, starting with sodium. And now we got to remember that the alkaline metal is the first group 1A. That's the other name for the 1A metals. Okay, so sodium would be would be the alkali metal in the third period. And in this case, the halogen in the second period, and obviously would be fluorine. Halogens are all group 7. In the second period, that makes it fluorine. And then a noble gas in the fourth period. First, we find the noble gas, which is the last group. And then we go fourth period, 1, 2, 3, and 4. Looks like that's krypton. Okay, sure enough. So krypton would be the noble gas in the fourth period. All right, talked a lot about metals and nonmetals, okay? And so here's a periodic table. Everyone in blue here are metals, okay? Where the nonmetals are shown in green color, starting with boron. So you start with boron, you go down to silicon, and you make a step down through here, and then step across. And step down, and then step across, and then step down, and then step across. And that's that stair step. First one is at an angle, but everything's all the other ones are stair step. Those are the metalloids. Okay, and then the reds are all non-metals. Not to forget hydrogen on the far left, which is a non-metal. Okay. Now, yeah, be able to distinguish this. Now, the metalloids, as I stated, are think of a mule. Anybody know where a mule comes from? How to make a mule? What's the combination of a mule to make a mule? Anybody have an idea? What category is Rachel? I can't read this. Is 117? That'd be that's unknown right now because it's just been isolated not too long ago, and they haven't figured out enough information. 117 probably be predicted to be a metalloid, but until they can get more samples to test it, because if you notice, you look. All the atomic weights that are in parentheses are radioactive, which means that they tend to break down pretty quick. and really not have enough material to determine properties. Okay. So as I was stating about metalloids, like a mule, which is a combination of a donkey and a horse, a mule has properties of a donkey, properties of a horse. So metalloids are like that. They have properties of a metal and properties of a non-metal. Used a lot. Some of these are used a lot in electronics. Silicon, for example, very important metal or metalloid used in electronics. Right. So, and then all the other ones. Now, it's important to learn who are metals and non-metals, because when we put these together, we're going to put point number one, all metals lose electrons, so we end up with a positive charge, okay? Let me repeat that. All metals lose electrons, we end up with a cation. All non-metals gain electrons, we end up with an anion. When we put a non-metal ion in a metal ion in a non-metal anion, cation ion, we make what's called a ionic compound. There's only two types of compounds that we're going to deal with. We call one ionic compounds, and the other one is molecular compounds. More on that down the road. But to be able to recognize you have an ionic compound or the other, as I mentioned, a molecular compound, is ionic compounds are made up of metal and non-metal combinations. Table salt, good old-fashioned table salt you put on your French fries. Sodium chloride. Sodium is a metal. Okay, it's in blue. Chloride is a non-metal. Okay, so it is what we call an ionic compound. And being an ionic compound, they have very specific properties, totally different compared to molecular compounds that are not do not have metal in them at all. Okay, so it's pretty straightforward using the stair step to determine who's a metal and non-metal. And as far as 117, you probably won't be asked any questions about these big elements. Okay. All right. Now, when we talk about the atomic radius, we kind of introduced this earlier when I said, okay, what would you predict as you go down the periodic table? Who's going to be bigger than the other? And then another element, and it's based on where they are in the periodic table. Okay. I always say as we go down the periodic table, we get bigger in energy levels. So it makes sense that the elements down at the bottom of the periodic table are bigger. The trend is going from top to bottom, the radius of the atomic size gets bigger. The radius is defined as the distance from the nucleus to the outermost electron or the valence electron. Okay, it increases as we go down the group. Okay, so obviously there's more energy levels, it's a bigger radius. Okay? Now, when we go from left to right in the same period, we find it's kind of counterintuitive. So, think about this, okay? As we go from left to right, or in this case, right to left, we find that the radius gets bigger as we go from right to left. Or, I tend to think of it from left to right. As we go from left to right, the radius gets smaller. And it's, again, kind of counterintuitive. But here's the thing, and the best way to demonstrate that is using the periodic table. As we go from left to right on the periodic table, the radius gets smaller. So we can predict that, for example, when we compare nitrogen to, say, fluoride, the fluoride radius would be smaller than the nitrogen. And within that group, lithium would be the bigger. okay? And neon within that group would be the smallest. So it's going from left to right, radius gets smaller. Now you might ask yourself, why is that? Okay. Now, unlike counter to going down the periodic table, because we're just increasing the number of energy levels, that increase in energy levels, the radius gets bigger, but the radius gets smaller going from left to right. And this is why. As we go from left to right within the period, if you look at this, what is increasing as we go from left to right? We're increasing the number of protons and we're increasing the number of electrons. So lithium has got 3 protons, 3 electrons. On the far right, you got neon that has 10 protons and 10 electrons. And so there's more what we call nuclear force as you go from left to right. There's more positive and negative interaction, okay? And that results in the more protons, more positive charge in the nucleus tends to want to pull the electrons closer onto itself. The best analogy I can think of is having a couple of magnets put together compared to a handful of magnets. And, if we put all these magnets together just right, the magnetic force is very strong in this handful of magnets as compared to over here when we got a couple of magnets, okay? And when that force is greater, then it starts to pull the electrons closer onto itself. And that is why, as we go from left to right, the radius decreases on the elements. Okay. As the positive charge increases, the electrons are pulled closer. So the atom is actually smaller. So, you might be asked questions, what is the trend from going from left to right? Please don't quote, well, it gets smaller. The question is why? Always why. Why is it smaller? And the answer is right there. Because we're increasing the positive charge as we go from left to right, which then causes the electrons to be pulled closer onto itself in the atom, and the atom gets smaller because the increase in nuclear force going from left to right. Okay. This snowman kind of helps you with the general trend as you go down the periodic table. You see how the snowman at the bottom is a bigger radius than the head, obviously. And if you take that snowman and just tilt him from to the right, that represents the diameter or the radius of the elements as you go from left to right. Okay, down, they get bigger, left to right, they get smaller because of the increase in nuclear force. Over here, just simply because of the increase of the energy levels, and that's why they get bigger. Okay, the fact that it gets smaller in radius as you go from left to right can also explain another property, in that keep this in mind, that the electrons are being held on tighter. That's why the radius gets sucked in and gets smaller. But if the electrons are being held on tighter, it's going to take a lot of energy to remove an electron, okay? Because they're being held on tighter as you go from left to right. And so a physical property we're going to talk about in a little bit would be explained because of the radius getting smaller. Here's a general trend. Obviously, nothing's 100%, so you're going to see some fluctuation here and there, especially down here where you get the inner transition metals. By that time, these elements are pretty big. So, the interaction of the electrons and all that, a little bit less because they're just big. So you'll see that their trend basically is, pretty uniform across the periodic table. But in general, when you get to the smaller elements, you can see that from left to right, how the radius decreases in size. Okay. All right, so question be asked, which is larger with respect to radius? You got O, SE, and TE. Well, to answer that, you first have to find them on the periodic table and how they related to each other. Well, in this case, they're both in the same group, specifically, not both, all 3 of them are in the same group. specifically group 7A, 6A. Okay, so they're in the same group, meaning they go down their periodic table. So it makes sense that TE is bigger simply because it's in a higher energy level. Okay. Now, with respect to magnesium, silicon, and sulfur, we're going to find them in the periodic table. They're all three are in the same period. So we're going from left to right. Okay. Which means that as we go from left to right, we increase the nuclear force from left to right, which means that the radius gets smaller as we go from left to right. So sulfur is smaller than silicon than magnesium. Okay. So magnesium is much bigger. All right. So there are videos on the website made by Dr. Kim. Gives you more information about this. Well, similar information. It's just another point of view and how to present the same information. So Dr. Kim has those videos. Do take a look at them if you have a chance. Okay, now ionization energy. And what we're doing here is we're measuring the amount of energy it takes to remove an electron from a neutral atom, from an atom, okay? So these atoms have these electrons around it. And there is a way to remove that electron, and we can measure that energy. So for what's happening here is denoted by the equation where you got the sodium, right here, sodium is undergoing a process where it's going to remove an electron and give us a cation, okay? So that's the ultimate goal here. If we're looking at the elements, is we're gonna hit it with energy and see how much energy it takes to remove an electron. Now, giving this some thought, you can probably start, get your thought process working. We just talked about how, as you go across the periodic table, that we have more nuclear force going on, which means that the electrons are pulled closer to each other, and therefore the radius gets smaller. So we could probably make a prediction that as we go across the periodic table, that for the elements on the right-hand side, it's going to take a lot of energy to pull off an electron, because those electrons are being held on to each other tightly. Okay, that's one thing to think about. Second thing is this: metals tend to want to give up electrons. Okay, so if I'm comparing metals and non-metals, then I can anticipate that the amount of energy to remove an electron from the metal compared to a non-metal would be much less for the metal, because they want to give up their electron quite readily. Okay, and then as we go down the periodic table, note that the radius gets bigger. So within the same group, though, I have one valence electron. That one valence electron in a large group, it's way out there in the boonies, so to speak. So if I look at the valence electron, let me bring you the periodic table. See, if I look at the valence electron of lithium compared to, say, potassium, notice something, that lithium's valence electron is in the third energy level, and potassium's valence electron is in the fourth energy level. And so potassium, being a bigger element, is not holding on to that electron that's further away to the nucleus than lithium, because lithium's electron is closer to the nucleus. So it's being held on with a tighter force. So I can predict that it'll be easier to remove that electron for potassium than it would be for lithium, because potassium's electron is being held further away than lithium, okay? And so we made predictions based on their position on their periodic table, okay? And the general trends that we have talked about. And so with that, we now hit it with some energy and we measure the amount of energy to remove an electron. Okay, and then we plot the data. Okay, so the IE was been found that the IE increases up a group because it's easier to remove an electron from a larger atom because that atom, that electron is further away from the nucleus. So it's not being held as tightly as a electron that's close to the nucleus, okay? And then the ionization energy, E, increases from left to right, okay? Because of a couple of things. One, on the left of the periodic table, we have metals. And guess what? Metals want to lose electrons. And so they're not holding on to the electrons as tightly as nonmetals. So metals, compared to nonmetals, would take less energy to remove an electron. The nonmetals are holding on to those electrons a little bit tighter, okay? Because because of the radius, there's more nuclear force going on, so those electrons are being held on tighter, and therefore require higher energy to kick one off, okay? Plus, those are nonmetals, and nonmetals want to gain electrons, not give them up, okay? Because they're holding on to electrons tighter, and metals want to give them up readily. So if we were to take a measurement of all the elements, what we see is the following table, okay? If we start with hydrogen, the far left, and then we go across to helium, note the hydrogen's ionization energy is somewhere around 14 energy units, whereas helium is about 24. Big jump from left to right. Again, helium's smaller. It's holding on to its electrons very tightly, plus the fact that helium has this duet fulfilled, so it's not going to give, it's inert, it's not going to give up its electrons. All right, so you start at helium, you go across, lithium's right here, you go lithium to neon. Okay, so lithium's ionization energy is about 5. And as you go across the periodic table, the ionization energy increases until you get to neon. Well, it makes sense. Again, you're going across from metals on the left that readily give up their electrons. And as you go across to the nonmetals, they're readily going to hold on to the electrons much greater than the nonmetals. So when you go in the direction of neon, the ionization energy goes up, okay? Until after neon, you go down to sodium. Sodium's right here. As you go from sodium across the periodic table to argon, you can see the energy level is a general trend again going across. It gets higher, but notice a trend. The slope of the direction getting smaller and smaller. For example, once we go from argon and we go potassium across to krypton, our trend still goes up, but not as steep. So we start getting our slope to get smaller and smaller. Because when we think about it, as we're going across the periodic table, we're also going down into larger elements. So as we go down to, element number, 40-ish here, the element gets bigger and bigger. And so those electrons that are further away from the nucleus are not being held on as tightly as those elements that are smaller in radius. So eventually, we will get into almost a flat line, where it's going to be very little difference. But there's still a trend of going from left to right, where it takes more energy to remove electrons from a nonmetal than it does from a metal on the left-hand side, okay? Yes, Teresa, the question is, are nonmetals holding on because they are smaller? And that is correct. Because the nonmetals being smaller, remember they're smaller because there's more protons and more electrons. So there's more nuclear force, which makes them smaller. The electrons get pulled in a little bit tighter. The fact that they get pulled in tighter makes them more difficult to remove them. Okay. They can be removed. Yeah, they can be removed, but it just takes more energy when you compare it to other elements. So you can see as we go from left to right, and in this case, how the slope goes very steep. So right here, we got lithium on the far left and go across the neon. You know, the elements going across the neon get smaller and it takes a lot more energy to remove them. But eventually, like I said, we get into an area where we basically have a flat line because the radius of the elements were down there in energy level 7, 6. They're big, you know, and the outside electrons are being shielded from the inside electrons, where there's a lot of them now. Okay, so it's going to take a lot of energy to get rid of an electron. Like right now for Chem 130, we say, you know, it's a side note. For Chem 130, we say that the noble gases are inert and they are unreactive. And that's a true statement, okay? However, when we get into the large noble gases, you know, those electrons are not being held on to the nucleus very well. So we can get those things to react, but, you know, it's a little challenging, but you can still get them to react. Anyway, but for Chem 130, noble gases are unreactive. All right, let's clear this up. Okay, which has a larger IE and why? So here we go. We got to first find them on the product table. And here we have them. They happen to be on the same group 3, period 3. Okay. And so we see the magnesium on the far left and chlorines on the far right. So two things to look at them. One, we have metals on the far left. Both magnesium and aluminum are metals. That in itself would tell you that they're going to give up their electrons a lot more readily than chlorine. Chlorine's a non-metal. Okay, so it's not going to give up your electrons as readily as the others. Okay. Second of all, chlorine is much smaller in diameter, like Teresa was asking here. Yeah, much smaller in diameter, so they hold on to the electrons much tighter because of the smaller radius, which is because of the increased number of protons and electrons. Okay, so in this case, IE, or the IE for chlorine, will be much greater than the other two metals. Okay. Taking a look at these, we are looking at elements within the same group, specifically group 1A. So they're all metals, okay? So being metals are going to tend to lose electrons, all right? But the difference is, you know, we have, as you go down the product table, the radius gets bigger, plus the electron gets further away from the nucleus, which means that an electron is being held on that's further away won't take as much energy as an electron that's closer to the nucleus, as in the case with lithium. So lithium, being smaller, is holding on to its electrons with a greater force than the larger atoms. So it would have a greater ionization energy than the other elements, okay? All right, again, we have ionization energy YouTubes. Be sure you read them and help you out with the information. And which brings us to the last property, and then we're going to call it a day. Now, this property is something that we need to really grasp because we're going to use this over and over again. And not to be confused with IE, which is the ionization energy of an atom, okay, of an element by itself, and how much energy it takes to remove an electron. Electronegativity is a measure of an atom's affinity for bonded electrons. Okay. Well, what do I mean by bonded electrons? Now, earlier I said, okay, we have to learn what are metals and non-metals, okay? Because when we put a metal and a non-metal together, they have a full charge, a full positive and a full negative. And they come together like magnets. Attractive. I don't have magnets here, but you played with magnets before. Put two together and they come together, right? There's an attraction to the magnets with each other, but there's a space between them, but there is an attraction. Okay. That is ionic compounds. Okay, that is the fact that I have a metal and non-metal and they come together like two magnets coming together. Earlier I mentioned about molecular compounds. Well, that's a little bit different. They don't come together like magnets. They actually make a bond. Okay, molecular compounds actually share a bond. Okay, and so one way to denote that is, let me change the color here, is I'm gonna write an arbitrary A, and then this line represents electrons that are being bonded between two molecules of A and A, okay? And those two are being shared as compared to, let's call this C plus charge and D negative charge, okay? This here, we call these ionic bond, where you have a metal and a non-metal come together and they have this electrostatic attraction because one has a positive charge and one has a negative charge. Okay. This one here, where they are actually sharing electrons, we call this a molecular bond. So this line represents two electrons. I can draw it with a line, or I can draw it with two dots like that. Each dot represents an electron. So one line represents two dots. And you're going to see me draw just lines. Occasionally you might see the dots come out, but it's much easier and quicker to draw lines. The point being is this is not an electrostatic attraction like the CD one, okay, like two magnets together. This is more of a sharing of those two electrons. So electrostatic would be coming together, a C and D, they just attract to each other. There's nothing being shared. Whereas, and that's an ionic bond. Whereas a molecular bond, there is an overlap and a sharing of an electron. There's a full-fledged bond, a true bond. Okay. Now, in the scenario where I have A and A together, these are two of the same elements, and so there would be an equal sharing of that line there, because A and A have the same electronegativity value. Now, when I put A and say, let's say B, I no longer have equal sharing because now I have two different atoms together to make a bond. And one of these atoms is going to pull those electrons more than the other, okay? And if this, a good example would be, say, a carbon and a nitrogen bond. I can draw C and then a line and then nitrogen. That's a carbon-nitrogen bond. That line still represents two dots or two electrons that are being shared. Now, the thing is here that the carbon or the nitrogen, one of these elements is going to pull electrons onto itself, okay, more than the other. And which direction depends on their position on the periodic table. Fluorine, which sits right here, approximately in the periodic table, is the most electronegative atom. And we use fluorine as our benchmark, okay, when comparing other elements. And then what we do is we say, well, how far away is the elements like carbon and nitrogen from fluorine? So carbon and nitrogen will be about right here. and the one that's closer is nitrogen. So that means that nitrogen has a higher EN, electronegativity, which means that it will pull more of those electrons in the bond onto itself than carbon. This sets up a special bond, characteristic of the bond, which we're going to talk about that. Oh, sorry about that. Somebody, give me 1 second. Okay, sorry about that. Anyway, and so what's happening here, electronegativity is a measure of the ability of an atom that is bonded to another atom to pull the electrons onto itself, which creates a special type of bond, okay? A bond that we call, say, a polar bond. When the atoms are the same, like the example of A and A, there's an equal sharing, and there is no pole. Now, what do I mean by pole? Well, think about it. Earth is a pole. We got a North Pole and a South Pole. Your battery has a pole, has a positive and a negative, okay? When there's an unequal sharing of a bond here because the difference electronegativity, then we create a pole in that bond. Specifically, we call it a polar bond, which affects the properties of that bond, which affects the properties of that molecule overall, which we're going to get more into detail as we get into the actual bonding of making the bonding of molecules and making molecules and putting structures together, okay? But this concept of electronegativity will show up again over and over again. And so, which has a big effect on molecules. All right, so the takeaway here with respect to electronegativity is that fluorine is the most electronegative element. Okay, so anything, if fluorine is bonded to anything, it's going to pull the electrons onto itself much more than any other element. Unless it's bonded to another fluorine, then everything's equal. Okay, think of electronegativity as a rope pulling contest. You know, if I get two people pulling a rope, equal weight, equal strength, it's a stalemate, okay? The rope's not going anywhere. All right, now, if I take another group and maybe I double the weight of one person, now that one person has an advantage. So that pull, that rope pulling contest, that's going to go more toward the heavier person, okay? And that bond is no longer equal, and it creates a special property on that bond. All right, so noble gases, again, noble gases, their octet is full and they're happy. A word about electronegativity, every element has a electronegativity value. And, you know, one could sit there and memorize, you know, electronegativity values, but it's not necessary because, again, when we know that fluorine has the highest electronegativity, and if we want to compare which atom is more electronegative that are not fluorine, we just use the fact that which one is closer to fluorine, because the trend is from left to right, it increases, from the bottom to up, it increases. So any element the element that is closer to fluorine will have a higher EN value when compared to another non-fluorine atom. Okay, like the example I just used, tried with carbon and nitrogen. All right, noble gases, of course, don't form bonds, and because the octet is fulfilled. So, guess what? You're on the row. Chapter 6. I am going to stop everything now.